Okay, and with that, it is my pleasure to introduce the next session, which is the one about PQ and messaging. So, as you know, the existence of a cryptographically relevant quantum computer is a threat to the things that we do. And you know what they say, when physicists give you a quantum computer, you make a post-quantum protocol. So today we're gonna look at some real-world deployments of PQ protocols. And actually, you know, you might have some nice improvements, whether the flavor of this is about efficiency improvements or stronger security guarantees. So it is my pleasure to introduce Mila. She's an applied scientist at Amazon Web Services, and she's going to talk to us about how formally verifying SHA-3 actually led to very important performance gains.
Hello, my name is Mila Anastasova. I'm an applied scientist at AWS. And today I'll tell you our journey for speeding up AWS's MLChem and MLDSA via optimized and formally verified SHA-3. Or today I'll tell you the story, verification accelerates. Every good story has an inspiring motivation, implementation details, and also impressive results. So today I'll tell you in this talk, why are we interested in post-quantum crypto with formal verification? I'll tell you the implementation details and how we achieved this in AWS LC. And finally, we'll discuss the real-world impact that we observed. Why are we interested in post-quantum crypto with formal verification in AWS LC? Let's first see what is AWS LC. Standing for AWS libcrypto, it is the general-purpose cryptographic library of AWS. It provides implementations in portable C and C++ of cryptographic primitives, and it also provides optimized target-specific implementations for some of the most widely deployed algorithms. In other words, AWS LC is the backbone for establishing a secure connection with AWS cloud services, providing the cryptographic primitives, the cryptographic implementations for ensuring data confidentiality, integrity, authentication, and non-repudiation. So let's see now where is AWS LC deployed. We decided to extract a single, among all the cloud services that AWS provides, we decided to extract data for a single AWS cloud service so that we can analyze the number and the type of connections that are being established. So in our specific service, we observed around 76 billion connections per hour. In other words, AWS LC is securing hundreds of billions of connections every single hour. Analyzing this data, we can say that every single algorithm optimization in such large scale deployment, it results in significant savings. In other words, we need our code, our implementation to be target-specific assembly optimized. On the other hand, assembly language is very challenging to write and review, and in such large scale, even a single bug, even a single error, it's too expensive. So therefore, we need some high assurance that our implementations are actually correct, or in other words, we need to formally verify the correctness of our code. Zooming in a little bit more in the data that we previously discussed, we have observed that 2.6 billion of these connections are post-quantum enabled, and this number is going to increase more and more as more services are transitioning to post-quantum crypto. So this means that we need to make sure our post-quantum implementations are fast and also formally verified for correctness, especially given that these algorithms are still relatively new. Let's see how SHA-3 is coming into the post-quantum cryptography picture. MLChem and MLDSA, standardized in 2024 by NIST, are already are provided in AWS LC. Both algorithms are module lattice-based post-quantum primitives, or in other words, they perform multiple arithmetic operations on multiple polynomials, normally represented or structured as vectors or matrices. In order to operate on this data, on these polynomials, however, first, of course, we need to generate this data. And this is where SHA-3 comes into the picture, or in particular, the underlying Keccak core permutation function, which is used as a pseudo-random function in this case. So to generate our example matrix over here, to generate each single entry, polynomial entry of our matrix, we need to call an instantiation of the SHA-3 algorithm. Okay. So let's see how we achieved fast implementation and formal in AWS LC. Let's see first how we can optimize, we can accelerate these SHA-3 operations. Modern processors, they offer more capabilities than simply operating on a single scalar operations. So therefore, if we carefully load for independent SHA-3 inputs, we can perform all 4 SHA-3 operations at the same time in parallel instead of sequentially. This means that all the data needed for MLChem and MLDSA, it can be generated in parallel, which significantly will reduce the time until data is available. In other words, we can generate all entries of our example matrix at the same time, at once. This, however, is going to result in our code being even more complex and difficult to write and read. So therefore, how can we actually make sure that this implementation, this aggressively optimized assembly code, is indeed functionally correct? In order to do so, we use the Hololite interactive theorem prover, which main feature is the very small kernel that it relies on. On the top of Hololite, there is the S2N Bignum library. It is an open source framework which provides different performant and also formally verified implementation of cryptographic operations. What S2N Bignum actually does is it models different architectures and microarchitectures, which allows us to verify our cryptographic implementations being functionally correct, memory safe, and also implemented in constant time. So how Hololite actually works, it checks for consistency between our machine code, the code that we're trying to prove correct, and a mathematical high-level specification of the function, of the algorithm itself. So let's see quickly how a Hololite proofs looks like. There is a set of assumptions and preconditions, which both should hold true before and at the very beginning of our program execution. In our example, as a precondition, we assign a given symbol to a specific content of a memory region, of a given memory region, at the very beginning of the execution of our program. In Hololite, we also have a set of postconditions, which basically need to hold true at the very end of our program execution. In our example, we check for consistency between the content of the same memory region against the formal specification that we have provided for our catch-up function applied on the original input data A. Hololite also allows us, or it requires that we specify the memory footprint of our function, which memory regions can be actually modified. And finally, we apply a set of tactics or transformation to our goal, which allows us to simplify and finally prove that our goal holds true, the postcondition holds true. So let's see what is the actual performance data that we have observed. We can see on the graph basically the timing required for performing one SHA-3 to 56 operation, where we can see that after deploying our scalar SHA-3 or catch-up optimization, we see around 10 and 15% of performance improvements. How this translates to MLChem? This time in the graph, we see the performance for the MLChem functions. After deploying our scalar optimizations, we see that this translates into between 7 and 10% of performance drop. Later on, we deployed our parallel AVX2 implementation of catch-up of the SHA-3 function, where we see up to 42% of performance speedup for MLChem 768 on different platforms, where this number actually goes up to almost 60% for MLChem 1024, based on the larger data that is being generated and processed. So in this table, we can see more details, like a breakdown of the actual performance speedup that we have obtained on different platforms, where we can basically see that for the higher security level of MLChem and MLDSA, the performance drops up to 60% for MLChem and almost 50% for MLDSA. So as a conclusion, do formal proofs actually allow for fast AWS-LC? We have seen that AWS-LC is deployed in such a large scale that it requires aggressive optimizations. Assembly code, however, it's very difficult to write and review. Therefore, we need high assurance for the correctness of our implementation. Therefore, yes, formal proofs are the path for fast and reliable code. Yeah, thank you for the attention.
Okay, thank you very much, Mila. I think we have time for maybe one question.
Thanks for the talk. I just wanted to ask, so these speed ups, do they also translate to energy consumption? So yeah, is it now more energy efficient?
It is definitely more energy efficient as well, since this is kind of the number, it represents the number of operations that are being done. We are using, for example, for the Scala implementation, it is just resulting in less instructions that are being executed anyways. For the AVX2, they're SIMD instructions, so they're a bit more heavy, but yeah, in general, yes, it does result in energy efficiency as well.
Cool, thanks.
Thank you.
All right, let's thank the speaker once again.